All right, so last time we talked about inscribed angles. Today we're going to talk about inscribed polygons. Remember, a polygon is just a shape that has segments that enclose space. So no curved edges, all the sides connect, all that stuff. Hopefully you remember. So a polygon is an inscribed, remember, which kind of sounds like inside. So that helps me remember what inscribed means. Kind of sounds like inside. So it is inscribed if all of its vertices lie on the circle. So hopefully you can see this triangle ABC, vertex A, vertex B, and vertex C are all right on top of that circle. Same thing for this quadrilateral ABCD, vertex A, vertex B, vertex C, and vertex D all lie directly on that circle. The circle then is the circumscribed circle. So circumscribed makes me think of circumference, which lets me know that we're going around the outside. Circumference, squeeze it in there. Okay, so all the vertices go around the outside of that circle. So some special properties that we have with inscribed polygons, specifically right triangles. If a right triangle is inscribed in a circle, then the hypotenuse has to be the diameter. It's the only way this is going to work. So looking at this diagram here, we can see that we have diameter AC here. There's a chord that goes right through the center of the circle. So AC is the diameter. So because of that, that tells me angle B must be a right angle. Okay, so if one side of the inscribed angle is a diameter, then the triangle is a right triangle. Another theorem we have talks about quadrilaterals. So a quadrilateral can be inscribed in a circle if and only if opposite angles are supplementary. So that means angle E and angle G here, they don't necessarily need to be the same, but they do need to add up to 180. Same goes for angle D and angle F. They do not need to be congruent, but they do need to be supplementary, so they do need to be able to add up to 180. So while other polygons, in addition to triangles and quadrilaterals, can be inscribed in a circle, those are the two most common that we deal with at this point in our mathematical careers. So a couple examples here. Example 7, we can see we have quadrilateral QRSP inscribed in that circle. Vertex Q, vertex R, vertex S, vertex P all lie on that circle. So because it is able to be inscribed, we know that we have opposite angles needing to be congruent. Okay, so I know that because QRSP is inscribed, the opposite angles must add up to 180 degrees. So if we solve this, that tells me the value of x must be 100 degrees. Okay, and then we also have angles P and R across from each other. And again, because they are in a quadrilateral that is inscribed, they must be supplementary. So they have to add up to 180 degrees. Okay, so y is going to equal 105 degrees. In example 8, if you want to pause it and try it on your own before you come back to see what your answer is, feel free to do that. So hopefully you were able to figure out that y would have to equal 112 degrees and that x would equal 98 degrees. The last couple examples here kind of deal with what we discussed earlier with inscribed angles. So what we talked about on Monday. So here, again, it's a two-parter. Again, if you want to pause it and try it yourself, feel free to do that and then come back and see what you got. So for part A, the measure of angle D has to be half of its intercepted arc, which is 100, and half of 100 is 50 degrees. For part B, they want the measure of arc AB, which I did highlight in the picture for you. So the intercepted arc that goes along with angle B would be arc AD. So if I do 35 multiplied by 2, that gives me 70 degrees. And we can see that DB is the diameter. So arc DAB would have to be 180 degrees. So that's why I put this here. And then I'm going to subtract out the 70 that we just found out. So that means the measure of arc AB would be 110 degrees. Let me know if you guys have any questions on anything.